This video is on Riemann sums, so go to the next spot in your notes and title it Riemann sums. I'm not sure how far we got in class because I'm recording this before this week starts, but at some point these notes are going to pick up, so pick up wherever we left off in class. Before we get further with Riemann sums, we need to review sigma or summation notation, because that's going to lead into the formal definition of the fundamental theorem of calculus. But before we get to that, let's just review this here. Once again, Riemann sums are used to approximate the area under the curve, when geometry cannot be used. Riemann sums are written in sigma notation or summation notation. These are the same thing. They mean the same thing here. Just realize sigma, this symbol right here, is a Greek letter, and it's the Greek letter S. So S, sigma, makes sense. Sigma or summation notation is a shorthand way of writing sums, or things that are added together, and sigma actually means to add. So you only use summation notation when you're adding things together. So this is what summation notation looks like here. You're going to have some kind of letter. It's called the index of summation. It can be any letter. So if you have an I or a K, these two are the same exact thing. You're going to have one number down here. This is your starting value. It's the first number you're going to plug into this I right here, or this K right here. It's the starting value. It's called the lower limit of summation. And then at the top of the symbol, you're going to put another number. That's your ending value. That's the last number that's going to get plugged into here. It's the upper limit of summation. I'm going to keep going with the I right down here. So this really means this thing right here. It's the sum of 2I from I equals 1. Oops, that should be a 5. To I equals 5. So going, oh boy, I don't want that. There we go. So going down right here, you're going to write this out, and you're just going to rewrite 2I over and over again. It's just you're going to keep plugging different numbers in. So you're going to start with plugging a 1 in. Then you're going to do 2 times 2, 2 times 3. You keep going until I is 5. You stop, and you add all these things together. Because it's a sum, it will give you 30. You can do all kinds of summation notations here. You could have the expression k squared plus 2. Here we're starting with 3. So 3 is the first thing you're going to plug into here. You do 4, 5, 6. You go up to 7. So here I have k equals 3, 4, 5, 6, and 7. You add them all together, and then you could evaluate this and get an actual number. But that's how summation notation works. Again, you're adding expressions together. So that being said, let's keep going with the Riemann sums here. Now in class, we covered the fact that if you have a velocity versus time graph, if you find the area under the curve or between the function and the x-axis, that's actually the total distance traveled. Now, if you have a nice, easy area under the curve, you can just use geometry. So you wouldn't need Riemann sums here. But if you have some kind of irregular shape like this, there's no geometry formula to find this red area. So what we're going to do is split it up into rectangles like this. Now, I'm going to do this more accurately in a second, but that's the whole idea because we don't have a single formula, so let's use rectangles to get as close as we can. So break region up into rectangles, add their areas. Pause the video and write all this stuff down here, and then I'll scroll down, and then I'll have you pause it again. There's 3 main ways to approximate the area. Using rectangles at least. There's left, right, and middle sums. Right now, we're going to assume that our function's continuous and positive, so above the x-axis. Let's start with an easy function. Now realize the function I have here is going to be this function right here. We could actually find the exact area using geometry. We don't need Riemann sums, but I'm going to do Riemann sums so we can compare our approximation with the true value. Whenever you do this, you're always going to have a starting value and an ending value on the x-axis. You're going to go in between them, and you're going to find the area under the curve between -2 and 6. So the way that Riemann sums for the left work is this. So let's start with the left Riemann sum. Before you go any further, can you pause the video and neatly draw this here? Again, neatness counts here. If you don't do this neat, it's going to look like a mess and it's going to be really hard to see what's going on. We have an absolute value function. The reason it looks like this is because -2 in parentheses means move right 2. +5 here means move up 5. And this negative in front of it means it's opening down, not up. So here's our V. We want the area from -2 to 6, so underneath this curve here. Again, we could use geometry and we could break up this area. It's really this whole chunk right here. And we could split it up into a rectangle and a triangle. And you could add those together and you could realize that the actual area is 24. Again, using geometry. Now let's use Riemann sums here and compare. This is important here. The left Riemann sums, you're going to choose the height from the leftmost value of the rectangle. We're going to start off always wanting rectangles of equal widths. So if I have a total distance here, -2 to 6 is 8. And let's say I want 4 rectangles. They're going to tell you how many rectangles you need. So I want 4 rectangles in a span of 8 on my x-axis. So that means every rectangle is going to need a width of 2. So what I did is I took a light blue pen and I split it up into 1, 2, 3, 4 rectangles. They all have a width of 2, remember. And the way Riemann sums work is, let me get my pink pen here, purple, whatever. You're going to go from -2 to 0 because that's my first rectangle. It goes in this interval. And you're going to do the leftmost side of this rectangle. Go up, touch the curve. Whatever height I have right here, that's the height of my whole rectangle. So again, left corner height. Now I'm going from 0 to 2 on the x-axis. So I go on the leftmost part of this rectangle, go up. I hit my function here. So I have a height of 3, height of 5, height of 3. These are my 4 rectangles. I have 4 individual sums, S1, S2, S3, and S4. I have that right here. And then I'm going to find the area of each rectangle. Well, that's easy because the area of a rectangle is length times width. So I'm really just doing length times width here, or height times width. So my width is 2 for all of them, and the height changes. It goes from 1 to 3 to 5 to 3, so it's 24. Notice that my approximation is actually the exact same as the true value. That's not normally going to happen, but if you look closely, it makes sense because notice on this part here when my function is increasing, I'm forgetting about this part of the curve here. I'm omitting that part and I'm omitting that part. That's going to happen when you do Riemann sums because that's not perfect. And then when my function starts to decrease, I'm adding on this area and I'm adding on this area. We really don't want this chunk here because it's not under the curve. But again, it's an error. We have to deal with it. Notice the 2 triangles that you omit will cancel out the 2 triangles you add on. So it ends up being perfect. Again, that does not normally happen. It's just a coincidence here. Now let's do some sigma notation. So I want to write this, adding these 4 things together with sigma notation. So you're going to need your sigma symbol. And our i's start at 1 and end at 4. So rectangle number 1 up to rectangle number 4. The upper limit of summation is always the number of rectangles you have. And I'm doing height times width. Well, my height is actually a function value on the curve. So my height for rectangle I, we're making it general, is equal to f of x sub I, whatever height I'm at here. And delta x is the width here. So delta x is the width, f of x is the height. So this is our sigma notation. And that's very important that you remember that because that's going to lead into the fundamental theorem of calculus very soon. So make sure you have that all written down, and let's keep going with the right Riemann sum. So this will go a little quicker now because it's the same process. You're just using different parts of the rectangle to get the height. So again, I'm using the exact same function. I still want to go from -2 to 6. We're doing right Riemann sums here, so make sure you have this written down before you move on. I'm choosing the height from the rightmost function value of my rectangle. So pause the video now, write all of this down, carefully draw this. Again, be very neat, put tick marks on your x and y axis so it's accurate. And let's see what's going on. Once again, I'm from -2 to 6. I want 4 rectangles. And 4 rectangles in a span of 8 on my x-axis means they each have a width of 2. So 1, 2, 3, 4. This time, whenever I split it up into 4 rectangles, -2 to 0 is my first rectangle. Instead of choosing the leftmost height, which would be here, I want the rightmost height, so the right corner, which is here. So this is the height for the entire rectangle. From 0 to 2, I'm going to go up to 2. It's my rightmost value. This is the height on the right, so it's the height for the whole rectangle. Same here and here. My area estimate will be the 4 rectangles added together, so S1 through S4. And again, I'm doing height times width. So like for the first one, the width is 2 and the height is 1, 2, 3. That's how I'm getting these numbers. Once again, I'm getting 24 here because the parts that I'm omitting, so I'm omitting that, I'm omitting this rectangle, or triangle, and I'm accidentally adding these on. Again, there's errors with Riemann sums. It's just an approximation. The stuff you add on cancels out the stuff you omit, so you end up being perfect in the end. Normally, the left and the right hand will not equal each other. Here's the sigma notation again. Same thing. We're going from 1 to 4 because there's 4 rectangles. Pause the video. Make sure you got all of that. And the last one. We can do left. You can do right. You can also do middle. I'm going to use the same function here. This time I want to go from -2 to 4. And this time I want 3 rectangles. And I want them to be evenly spaced. So pause the video right now and write this stuff down and draw this graph here. Now if I want 3 rectangles evenly spaced from -2 to 4, that's a span of 6 on my x-axis. And I want to keep them with a width of 2. So if they each are going to have a width of 2, I'm going to have 3 rectangles like I said before. So the way that the midpoint Riemann sum works is you're going to choose the function, that should say value, function value at the middle height of the rectangle. So I'm going to do this one with you right now so you can see how it's done. Here are my 3 rectangles, and I'm going from -2 to 0, and the middle x value is -1. So you're going to go up and hit the function right there. Whatever height you're at, that's going to be the height for the whole rectangle. Now I'm from 0 to 2. The x value that's in the middle is 1. So I'm going to follow 1 up. And I have a height here that happens to be 1, 2, 3, 4. So that's my rectangle for the whole thing. So I have this rectangle. And from 2 to 4, the middle value is 3. So scoot up here, stop right there. And here's my 3rd rectangle. So I have S1, S2, and S3. So they each have a width of 2. This one has a height of 2. This one has a height of 4. Whoa. 4, and this one has a height of 4 as well. So let's find what the sums are. So my approximate area is, S1, S2, S3 all added together. So I have 2 times 2 plus 4 times 2 plus 4 times 2. Again, my height times my width. That's how you find the area of a rectangle. It's 20. You could use geometry and get the actual true value. The reason you can use geometry again is because these are all shapes that we can split up. So we could have like a rectangle here and a triangle, a square, and a triangle to find it exactly. But again, we're doing Riemann sums just to practice them. And here's the sigma notation this time. I'm going from 1 to 3 now because I only have 3 rectangles, and it's f of x sub I. That represents the height of a rectangle, and delta x is the width of each rectangle. So make sure you have this all written down, make sure it's neat, and we will practice this in class next time I see you.